Good afternoon all. Today we will be doing pasting properties. So myself Ganga Kishore, I will be explain how to do this, and this is Shubhanki ma'am. She will be explaining how to demonstrate this. Okay, she will be helping with operating. Okay, now first coming to this is pasting properties, right? So what is a pasting property? Why it is needed? You have to know basically to start this. What is a pasting property? So we take some flour. We will have some flour, right? So when we do pasting property, what will happen? It will indicate the molecular breakdown of that flour. So we will be having flour, we will be adding some water, obviously some gel, we will be heating. I will explain. We will be heating, right? So obviously some gel going to form or some paste is going to form, right? So we will be studying the characterization of this paste, how paste will be there, and what is the stability of the paste. Those things and all we will be studying through this pasting property. Okay, so this is the equipment what we are using. This is the rheometer. Model is MCR 302E. Okay, and bar Austria model. Okay, this is the make and model for this equipment. Okay, now next is you have to know how it actually runs. First I will say the procedure, then actually how it proceeds I will be explaining. So I have taken 2 gram of sample, 20 ml of distilled water. 2 gram of sample and 20 ml of distilled water. This is the canister, okay, where we will be adding this 2 gram of sample and 20 ml of water. After adding, I will be placing in this sample holder. Okay, after placing, I will be locking it. Then this is the blade that will be keep on rotating. It will enter inside. There is a provision for closage. We will be closing that. After that, we will be starting the experiment. Once it start, what actually it happens, let me say. Now, once we give start, first it will go to 50 degrees Celsius. Okay, it will go to 50 degrees Celsius. In 50 degrees Celsius, it will stay for 1 minute. Okay, then from 50 to it will start. Once we will be giving heat, right? So from 50 it will go to 95 degrees Celsius. At 95 degrees Celsius, it will be stopping for 3 minutes. It will be maintaining. Then from 95 to it will come to 50 degrees Celsius. In 50 degrees Celsius, it will be maintaining for 2 minutes. Okay, it will go up and come down. Okay, this is the procedure what will happen. Okay, now you are got it, right? So what you will be getting out of this is, first is you will be getting peak viscosity, breakdown viscosity, setback viscosity, final viscosity, peak temperature, peak time, pasting temperature, and holding strength. These are the things you will be getting out of this pasting property experiment. Okay, now what is a peak temperature? What is a peak temperature? Peak viscosity, those things and all I will be explaining now. Okay, first is peak viscosity, let it take. What is the peak viscosity? When obviously from 50 we are heating to 95, right? The maximum viscosity that is reached when we are heating, that is known as peak viscosity. Okay, then what is the final viscosity? Final viscosity is the final one. So obviously first we will be heating, then we will be cooling. At finally after cooling we will reach one viscosity, right? That is nothing but a final viscosity. Okay, gelatinization, pasting temperature, those things and all you will be knowing. We will be, once we give heat, what will happen? If they say some starch sample is there, it will obviously gelatinize. At particular temperature, it is getting gelatination, right? Gelatinized, right? That is nothing but pasting temperature. Okay, now you are clear with what is what, right? So we will be doing, showing how we have to do that. Okay, as I told, first we have to take the canister. I am adding sample to it. I have added 2 grams of sample to it. Okay, then I have I am adding 20 ml of distilled water to it. Actually we know exactly. Now I am mixing. We should not use some metal or something because it might scratch the canister. Some scratch might happen, so I am using only this silica one. So now I have mixed well, so I will be placing here. Okay, after placing I will be locking it so that it won't move. Now ma'am will be bringing that blade down. There is a provision for bringing up down and for bringing up. Okay. Okay, now blade had went inside, so I will be closing this. So that it won't spill outside, so I am closing this. After that we will be starting only. Okay, what happened, I told na, temperature will, it will heat, then it will cool down. That procedure will happen, then it will give result. It will approximately take 23 minutes for running this. Yes ma'am. If you have any query, you can ask me. You got the procedure, right? How we are doing, what we are finding from this, everything you got it, right? Flour will be there. Once we are doing molecular breakdown will be there. We will be testing the characterization of viscosity and stability from this. That is from for that paste or gel what is formed. That's the thing we are doing here. Okay. It will take 23 minutes. How the results will be coming, we will be showing a model for you. It will be keep on running only in background, but for it takes more time, so I am showing the result, how the results will be. Can we adjust the RPM of the transition, or it is fixed? This rotation speed, that is fixed one. That we won't be changing.
What software you are using? The same software for your
Rio Compass, yeah.
The unit of viscosity is only in centipoise only. So previously we measured the viscosity in Pascal second.
It will come in MPa, I guess. MPa second.
It will become centipoise viscosity unit. For pasting property, we observe viscosity as a unit of centipoise, or we use another unit.
Just if you want, you can convert it. Okay, you can see the result here, right? As I told, you can see peak viscosity here, peak time you can observe, pasting temperature you can observe, holding strength you can observe, breakdown viscosity, final viscosity, setback viscosity. Two things you will be getting: setback from peak, setback from trough. Those everything you can get from that, and you get a graph also. Either with this reading you can plot a graph or give us a table. Based on your requirement, how you want to present the data for a paper or something, you can give accordingly. Say you are developing a fish pastry, something. Say fish patty, something you are developing. Okay, you have to see pasting property of that. So you can study using this. It will be very useful for that. Or some you are extracting some fiber from some sea product, you can use this for testing what will be the pasting properties of those things. It will be useful for that. Rheology and pasting is one of the important study because every food industry will be using one or other way. So you got it right, how graph will be and what are the results we can get from it. So it will be running for next 23 minutes, and after that what results we are going to get for our sample, you can note down that reading. Okay.
So first of all, good afternoon all. So yesterday we have started with our chitin extraction procedure. Okay. So you know, like anyway, if somebody can explain like what you have done. Even already sir explained before last lectures. So you might be knowing like what all procedure or what are the steps we have to do. So for example, for those who are came today, so they will be not familiarized what we have done yesterday, right? Isn't it? Okay, so so for those we will explain once again what we are going to do. So first of all, we collected 3 different samples. So due to the lack of time, will be only having 2 samples. The first one is we took only 2 samples. First one is crab and second one is shrimp. Okay, crabs and shrimps. Okay, so both of them we collected in the sense the shell of this animal collected, and we have undergone drying process, and after drying the moisture content reduced as much as possible. After that we have gone for next step. What is the next step? Demineralization. For demineralization we have used HCl and acetic acid, and citric acid we didn't use, and one organic and one inorganic acid we have used. And after that, after demineralization, what is the next process? Deproteinization. Okay, deproteinization. For deproteinization, as we know, every protein having their own isoelectric pH. Okay, so some protein, especially these shrimp or crab protein, mostly soluble in which medium? Alkaline medium. Okay, so we are preparing this medium as of now. So 0.5 normal NaOH we will be having. So NaOH can be used for demineralization as well as huh? Deproteinization as well as for what? Deacetylation. Okay, so HCl we have used for demineralization. NaOH initially we are used for deproteinization. So the protein, so if we want to extract the protein, so after washing with the NaOH we can dry it. Okay, after washing with NaOH we can dry the mass, and we will be getting alkaline soluble protein fraction. Okay, we can write and we will be getting the protein. So if you want to characterize the protein, we can check like what are the isoelectric pH of the proteins and what are the properties of the protein. Whether even usually you might be knowing like animal proteins are albumin or globulins or any other matrix. Albumin or globulins usually. What it should be? No. Albumins or globulins. Shells protein usually globular protein or not? Okay, globular protein. So the globulins usually is dissolved in alkaline pH. Okay, and this protein we will be separating, we will be drying it, and initially after demineralization, this HCl soluble portion, okay, that the acid soluble fraction, if we want calcium chloride, we can dry it and we will be getting calcium chloride, because calcium carbonate which is reacted with any acid, we will be getting their chloride salt, right? Okay, so if, for example, if we will be using HCl, we will be getting calcium chloride. If you are using acetic acid, then we will be getting calcium acetate. Okay, so this for making the uh, calcium chloride, we also already kept it for drying. We will be showing this dissolved fraction for your better understanding. It will be in different color because we didn't go for pigmentation, depigmentation. Okay, so astaxanthin is the major pigment which is present in the shells. Okay, so we does not go for the pigmentation. So some of the pigment may dissolve in acid, so that's why the color is like brownish in nature. Okay, so in acidic pH the color, even with respect to every color which having different chroma factor with respect to the pH in presence of H plus and OH ions, the color will vary according to the pH. You might be knowing about this anthocyanin. It varies its color with respect to pH, right? When blue to purple color. Okay, that wide range of color or chroma is there in presence of hydrogen ion concentration. Similarly, astaxanthin which shows this brownish color in presence of acidic pH, and this pigment also dissolved in the fraction. So now we are going to do washing of the dissolved fraction in order to remove. Why we are going for washing here? What's the need of washing? After mineralization, demineralization? Remove the HCl, okay. So for removing the HCl, we will be going for washing. Some fraction I have washed because we don't have enough time to wash continuously. So anyway, I will show you how to clean it, and after removing the debris and other matter, we will be washing and we will be taking the dissolved fraction. So whenever we are adding acid to any shell, how we can say that it is completely demineralized? How we can say it? For example, it's a hard shell. When we are adding acid, how we can say it's demineralized? Any idea? It becomes softer. It becomes softer. Okay. So it becomes softer. I will show you like the original one and how it's changed. Okay. It becomes so flexible because chitin is flexible in nature. But even in presence of calcium carbonate and chitin network, it's a cross-linked polymer. Okay. So the cross-linked network giving the strength or rigidity to the shells. Okay. So in order to protect from extraneous matters and other extraneous environment. So this washed washed with water, these shells, what we are going to do? What's the next process? We will be treating with NaOH for deproteinization. So we will be drying the fraction again, and after that again we will be treating with the next concentration of NaOH at a higher or elevated temperature for the deacetylation. Okay, so deacetylation means this acetyl group is there, we have to remove the acetyl group, so the chitin will convert it into chitosan. Okay, so that's a process, that's what we are going to do. Anyway, NaOH we will be treating and we have to keep for the overnight, then only it will convert it into chitosan. Then we will be taking the sample and we will be drying it, we will be getting the chitosan, and the chitosan can be dried and we can go for other characterization. Okay, and the protein characterization also we can do if we are getting enough fraction of protein. Okay, so even it will be solubilized with the NaOH, and the NaOH fraction will be there. So the sodium hydroxide also need to be removed. Okay, for that we have to wash it again and again. We will be precipitating with isoelectric focusing, or isoelectric precipitation can be done. So we will be adding acid slowly, and once the fragment which is dissolved or precipitated down, the fragments can be centrifuged and we will be getting the protein fraction. So whenever we have any plant proteins, okay, so you might have tried, even for example initially we will be going for the literature, previous literature. So you might be knowing like what is the exact isoelectric point of the particular protein. So if we are not knowing the particular isoelectric point, how we can precipitate it? We will be slowly adding. Anyway, most of the proteins from plant sources having an isoelectric point which is ranges between 3 to 6. Okay, so at 6 or at a neutral pH, we will be neutralizing the pH of the particular media. Then we will be slowly adding acid. Okay, so at a point it will be clumped or coagulated. For example, dairy products. Okay, so for example, when we are adding citric acid slowly we are adding citric acid, it will be at a point it will coagulate and we will be getting the casein, coagulated calcium caseinate. Okay, or the casein fraction we will be getting. Okay, that will be pressed, then we will be making the paneer, or if you want to go for cheese, there is another set of processes are there. Similarly, here also we will be precipitating the protein fraction by using isoelectric point. That we can do in the next day because we have to keep it for drying for the overnight, all these different fractions. So shall we continue? Shall we continue the practical section? Okay, so anyway you will be having class at 4 o'clock. So meanwhile we have to finish this portion. Okay. So yesterday as we have already prepared, already kept it for demineralization. Okay, so the sample for shrimps are here. So you can see it is completely dissolved. The color is turned and it becomes so soft. Okay, fine. And here as you can see that the crab shell, as you know, like crab shells are so harder. Okay, and you can see how soft it is. See, you can see how soft it is, and it becomes so soft. and because of demineralization. So most of the calcium carbonate which is separated, like it is react with the hydrochloric acid and form calcium chloride, and the carbon dioxide, as you can, yesterday we have seen that is releasing in between. Okay, so this is demineralized crab shell. Okay, so now we are going for the proteinization. Before that we have to wash it. So as we have already washing solution is there, so I have partially washed this thing, so that's why it looks somewhat better than these samples. Okay, so anyway, like how we can wash it, because whenever during washing, if we are directly washing with the normal water and just throwing it, it doesn't remove all the dissolved matrix or dissolved acids. So we have to mix it properly and keep it for some times. And if we are heating slowly, like the acid matrix or acid fraction can be easily separated out. Okay, so for that we can mix it properly, and we have to remove the other debris which is attached to the shells. Okay, so you can do it. And transfer to here. Okay, transfer it to here. So apart from that, as you can see, for yesterday we already dissolved this shell in the HCl, and it's look like this. Okay, so what is the composition? You can guess. It's containing calcium chloride, and some pigment might be there, and others matters also there. Okay, so that's why the color is looking like this, and we will be drying it anyway today, and we will show you tomorrow what will be coming, and we will check for how much concentration. For example, for doing, as sir already told, for mass balance we have to evaluate the concentration of calcium chloride, as well as when we don't have carbon dioxide sensors. So if we have carbon dioxide sensors, we can also evaluate from the amount of carbon dioxide which is separated, or amount of carbon dioxide which is released from the particular shells. Okay, so after that, after proper washing, we got it, and sorry. So now we are we can take any concentration of NaOH, but we are not going for higher molarity of NaOH. So now we are preparing 0.5 molar, 0.5 normal NaOH. So how we can prepare 0.5 normal NaOH? For 1 normal NaOH, what is the amount? 100 ml. Okay, then in 1 liter 40 grams. So 0.5 normal, then 20 gram in 1 liter. Okay, so we already measured this NaOH. Even for example, whenever we are preparing NaOH for standardization or titration, we have to standardize the NaOH anyway, because NaOH is highly hygroscopic, because it's already anhydrous, right? So that's why we have to titrate it against citric acid, and citric acid is not that much hygroscopic in nature. So if we are titrating against it, then we have to standardize what is the amount, whether it is less than 1 normal or greater than 1 normal. Accordingly, after standardization we will be preparing. But here the major aim is to deproteinization. So even if it is 0.5 or 0.6 normal, it doesn't matter. Whatever it is doesn't matter, and we can prepare it properly, and we have to, the major focus of our addition of NaOH is to deproteinize the fraction or the shells. Okay, so we can go for that. We can add the NaOH in this, so and we can keep it for overnight. Okay, so after that, even during night time, anyway we have to keep it for nearly 4 to 5 hours. After that, we will be taking the supernatant or the liquid fraction and we will be drying it overnight. Meanwhile, we will be adding one normal NaOH into it, and again we are keeping it in an elevated temperature, nearly 60 to 70 degrees Celsius in oven, because that cannot be demonstrated during night time. Anyway, we will be adding the one normal NaOH during night and we will show you what we will be getting tomorrow. Okay, so we will be grinding it, and possibly if it is dried before afternoon, we can take the same chitosan for the FTIR analysis, or we will be taking some other already extracted chitosan sample for the FTIR analysis, and we can check like what kind of graph is we getting and whether it's if the graph having any variation from the pure chitosan, then how we can differentiate it in FTIR. Any idea?
Fraction.
Any other fraction if it is present in this chitosan? It's not 100% pure. If some impurities are there, then how we can identify it? There should be some other functional group, okay, apart from the particular functional group which belongs to chitosan. So we can easily differentiate that there are some other functional groups are there. So that's why the graph will be varying. Some other functional group, so peak, if we are correcting the peak, then there should be some other group will be there. If any group which belongs to calcium hydroxide or some other fraction is there, then we can say it is pure chitosan. Okay, so like even chitin and chitosan, when any acyl group is there, then what is the final conclusion? If any acyl groups are there, then it's not completely deacetylate. Okay, deacetylation is not properly done, so we can find that we have to add more NaOH and need to keep it for a long time. Okay, so from that we can estimate that the acetylation is not properly done, like that way. Okay, so now we can add the NaOH and keep it for almost 4 hours in oven. Okay. So if the water color is also somewhat different, so it may also contain some water soluble protein fraction. Okay, small amount, or even we have kept it for high concentration of HCl. So definitely some of the protein which is denatured. Okay, so denatured fraction might be also there, like some peptides and all. If you are taking the peptides, if you are going for some antimicrobial studies, it may show some better antimicrobial properties. Okay, so that can be also done. It may also contain some peptides, water soluble. When some peptides are highly water soluble in nature, because like it is a single chain, not coiled one, or maximum it might be having secondary structure. It don't have tertiary and quaternary structure. Okay. So we will be adding the NaOH. It is 0.5 normal NaOH is there. You can see it's almost completely dissolved, and we will be adding it into these shells for the deproteinization. Not fully, like half or half. Okay. So we have added, and we can see like even the color might be changing, and some if acid fraction is there, it will be reacting, and again gas bubble will be going. So some dissolved gas bubbles will be present in the vacuoles or in between the cells, that also will be releasing. And as by tomorrow we can see like even the protein which will be separated. So the white fraction will be there. So we can see like the protein which is dissolved in the NaOH solution. Okay. So that's why we have taken almost 0.5 normal, and if you are taking 0.2 normal and all, the rate of dissolution will be lesser. Okay. So that's why we have taken 0.5 normal, and tomorrow we will be separating the fraction and we will be kept it in a Petri plate and we will be drying it. We will be getting the protein fraction and we will be checking for the purity of the protein, because it may contain other impurities. It won't be 100% pure protein fraction. Okay. So that can be also done. Okay. So now we will be keeping it for some 6 to 7 hours, and night we will be separating and we will be keeping the liquid fraction for protein collection, and the remaining fraction we will be again adding NaOH, 1 normal, not 0.5, 1 normal NaOH, and we will be keep it in for overnight in incubator for the 60 to 70 degrees Celsius. Tomorrow we will be getting some, not completely, like up to a level the deacetylation can be happens. Okay. So we will be getting chitosan. Okay.